NASA, the renowned space agency, has just unveiled a groundbreaking propulsion system that could revolutionize space travel as we know it. It seems to defy the laws of physics as we understand them. NASA's latest creation promises to propel spacecraft at near-light speeds, a feat previously deemed impossible. But what exactly are the key features of this near-light speed engine? And how does it differ from traditional propulsion methods? And more interestingly, what potential applications does this technology have for future space exploration missions? Join us as we unravel how NASA has just designed a near-light speed engine that breaks the laws of physics. The future of humanity relies on finding a new home beyond Earth because our planet won't remain habitable forever. However, the task of traveling through space to reach another planet is incredibly discouraging due to the vastness of the universe and the sheer size of our solar system. To make space travel possible, we need to develop engines that can propel us at unimaginable speeds, far beyond the limits of conventional engines. Some researchers have proposed designs for engines that defy the laws of physics, allowing for travel at speeds faster than the speed of light. Alpha Centauri, our closest stellar neighbor, sits at a distance of approximately 4L367 light-years away from Earth. This means that even if we were to embark on a spaceship traveling at an astonishing speed of 100 times the speed of light, it would still demand a staggering 4.367 years to reach this distant star system. When it comes to conventional rocket propulsion, the main setback lies in the enormous amount of fuel required to traverse the vast cosmic distances. Rockets rely on chemical reactions to generate driving force, which means they must carry their own fuel on board. This results in significant weight and volume constraints, limiting both the range and speed of spacecraft. Additionally, the sheer scale of the universe presents a demoralizing challenge for space travel. Space is vast and largely empty, making it difficult to navigate accurately over such vast distances. Even minor errors in track calculations could result in missing a target by millions of miles. Despite these challenges, scientists and engineers are constantly exploring innovative solutions to enable faster and more efficient space travel. From advanced propulsion concepts like ion drives to theoretical concepts such as warp drives, researchers are pushing the boundaries of our understanding of physics to make space exploration a reality. Even though rockets have been the backbone of space exploration, they come with limitations, especially regarding speed. We need propulsion systems that can provide significant drive without the need for carrying excessive fuel, as refueling isn't an option in space. Fortunately, there's an engine that seems to defy conventional physics. It's called the M-Drive, or impossible engine, because it promises to do what was previously deemed impossible. Unlike traditional engines, the M-Drive doesn't rely on burning fuel to generate drive. Instead, it operates by exploiting electromagnetic waves to propel a spacecraft forward. What's even more astounding is that it produces no exhaust, making it a clean and efficient option for space travel. It's like plugging in a device, flicking a switch, and zooming off into the cosmos. So how does this M-Drive actually work? At first glance, it might resemble a traditional rocket engine, but there's a key difference. It doesn't have any visible openings. Instead, it operates by bouncing microwaves around inside a closed chamber. This bouncing motion of microwaves within the chamber is believed to create a propulsive force, essentially pushing the spacecraft forward. This is quite remarkable because most forms of rocket propulsion rely on the principle of conservation of momentum. In simple terms, to set a spacecraft in motion, you need to push against something. For instance, when you jump, your feet push against the ground to propel you upward. Similarly, airplanes push against the air to lift off, and rockets rely on the expulsion of exhaust gases to generate force and propel themselves forward, along with their payloads. However, the M-Drive seems to challenge this fundamental principle of rocketry. Instead of relying on the expulsion of matter to generate force, It purportedly generates force directly from electromagnetic radiation. This revolutionary concept has baffled scientists and engineers since its inception. Moreover, the M drive has been a subject of skepticism and controversy within the scientific community. While some experiments have reported positive results, others have failed to replicate these findings, leading to debates about its validity. Despite the skepticism, researchers continue to explore the potential of the M drive and its implications for future space exploration. The M drive was first proposed by British scientist Roger Scheuer in 1999. It generated significant controversy and skepticism within the scientific community due to its purported violation of the law of conservation of momentum. One of the most notable aspects of the M drive is its lack of propellant. Traditional rocket engines rely on expelling propellant to generate drive, but the M drive claims to produce drive without expelling any propellant, seemingly defying the laws of physics. Numerous experiments have been conducted to test the M drive's capabilities, with some researchers reporting positive results showing drive generation. However, these results remain controversial, as they have not been consistently replicated by independent experiments. The underlying mechanism behind the M drive's purported drive generation remains a topic of debate. Some theories suggest that it may involve interactions with quantum vacuum fluctuations or the generation of asymmetric electromagnetic fields. Despite the skepticism surrounding the M drive, its potential implications for space travel are significant. If proven to work as claimed, it could revolutionize space exploration by enabling spacecraft to travel vast distances without the need for large amounts of propellant. However, further research and testing are needed to confirm its validity and understand its underlying principles. Since its inception, numerous research groups around the world have attempted to replicate Scheuer's findings and test the feasibility of the M drive. While some claim to observe a slight net force in their experiments, the effect was so tiny that it raised doubts about its practicality for space travel. Critics argue that the purported force observed could be attributed to experimental errors or external factors rather than a true propulsion mechanism. Despite years of experimentation, the M drive continues to be a subject of controversy and skepticism within the scientific community. Many researchers remain unconvinced of its viability, citing the lack of a comprehensive theoretical framework to explain its operation. Moreover, the absence of a clear understanding of the underlying physics raises doubts about its potential for practical applications. Nonetheless, proponents of the M drive remain hopeful that further research and advancements in our understanding of physics could unlock its true potential. The possibility of exploiting previously unknown phenomena or uncovering novel principles of propulsion keeps the intrigue alive, fueling ongoing investigations into the mysterious workings of the M drive. There exists another remarkable technological marvel that transcends the boundaries of possibility. One such innovation is the ion drive, a propulsion system that harnesses the power of ions to propel spacecraft through the cosmos. Initially relegated to the realm of science fiction, the concept of the ion drive was met with disbelief when first introduced. Critics doubted its feasibility, questioning whether such a system could ever generate enough force to move even the smallest spacecraft. However, behind the veil of skepticism, scientists persisted, driven by the audacious belief in the power of human imagination and innovation. The breakthrough came when researchers discovered that by accelerating ions to incredibly high speeds using electromagnetic fields, they could produce a continuous and efficient force. This revolutionary propulsion method, once deemed implausible, began to take shape in laboratories around the world. The ion drive operates by expelling ions at high velocities, creating a reaction that propels the spacecraft forward. Unlike traditional chemical rockets that rely on combustion and expendable fuel, the ion drive utilizes a steady supply of electricity to ionize a propellant, such as xenon gas. This process results in exhaust velocities far greater than those achievable by conventional means, allowing spacecraft equipped with ion drives to achieve remarkable speeds and travel vast distances with minimal fuel consumption. Despite its initial skepticism, the ion drive has proven its worth in numerous space missions. NASA's Dawn spacecraft, for instance, utilized an ion drive to explore the asteroid belt and study the dwarf planet Ceres, demonstrating the effectiveness of this innovative propulsion technology in deep space exploration. As our understanding of ion propulsion continues to advance, so too does its potential for future space missions. Beyond its initial conception, this revolutionary system has roots that stretch back to the mid-20th century when scientists first began exploring the potential of electric propulsion systems. One intriguing aspect of the ion drive's development is its reliance on solar power. By harnessing the virtually limitless energy of the sun, spacecraft equipped with ion drives can operate for extended durations without the need for conventional chemical propellants. This not only reduces mission costs, but also opens up possibilities for deep space exploration where traditional propulsion methods fall short. Moreover, the Hall effect force, the heart of the ion drive system, operates on a principle discovered by American physicist Edwin Hall in 1879. This principle involves the generation of an electric field perpendicular to both the direction of current flow and the magnetic field. Harnessing this effect allows for precise control over the acceleration of ions, resulting in highly efficient propulsion. In addition to its applications in space exploration, the ion drive technology pioneered by Aerojet Rocketdyne has found utility in satellite propulsion systems. Satellites equipped with ion drives can adjust their orbits with unparalleled precision, extending their operational lifetimes and enabling missions that were previously impractical. The ongoing refinement and advancement of solar electric propulsion systems hold promise for the future of space exploration. It is also found on various spacecraft, such as NASA's Dawn probe currently circling the dwarf planet Ceres, representing cutting-edge propulsion technology. These forces utilize an innovative method called ion propulsion, which involves expelling ions to generate force. While not as swift as traditional engines, they boast remarkable fuel efficiency, making them ideal for long-duration missions. However, they transfer momentum to spacecraft at a gradual pace. NASA is considering employing a similar propulsion system known as the Solar Electric Propulsion SEP drive for future missions to Mars. The primary challenge with ion drives lies in their relatively low force output. Nonetheless, advancements are continually being made to enhance their performance. In another stride towards space exploration, NASA has implemented a high-power electric propulsion system for the Lunar Gateway, a space station slated to orbit the Moon. Recently, in April 2021, NASA successfully activated an upgraded ion thruster system, which promises about 30% more power compared to its predecessors. This development signifies a significant leap forward in the world of space propulsion technology, paving the way for ambitious lunar missions and beyond. NASA began exploring a different way to send spacecraft swiftly to their target locations called nuclear pulse propulsion. This was happening around the same period when nuclear jet engines were being created for bombers. There was also some curiosity about using nuclear reactors to provide power to spacecraft. One notable advantage of nuclear reactors in space is their ability to endure the freezing and shadowy expenses without depending on sunlight. Moreover, they are highly dependable. For instance, the Zeus reactor is engineered to function for a remarkable 10 to 12 years. With such durability, it could significantly shorten the time needed to transport spacecraft to distant planets. However, navigating the vast expanse of space comes with its own set of challenges, particularly when it comes to propulsion systems. While highly enriched uranium proves capable of withstanding the blistering temperatures required within a nuclear reactor, its use raises serious safety concerns. The potential risks associated with its handling and disposal are significant considerations in the world of space exploration. Furthermore, recent developments have cast further doubt on the viability of this propulsion method. The United States, a key player in space exploration, has taken a decisive stance by prohibiting the use of highly enriched uranium for propelling objects into space. This prohibition underscores the growing agreement within the international community regarding the need for safer alternatives in space travel. The search for alternative propulsion systems continues unabated, driven by both safety concerns and technological advancements. Researchers are exploring innovative solutions that offer the necessary force without the inherent risks associated with highly enriched uranium. From ion drives to solar sails, the possibilities are as diverse as they are promising, signaling a new era of exploration and discovery in the cosmos. Russia is getting ready to send a super-advanced spaceship into space, and it's going to be powered by nuclear energy. This spaceship is going to be so cool. It's going to start its journey from the Moon, then head to Venus, and finally make its way to Jupiter. The Russian space agency, Roscosmos, has announced that this special spacecraft, called a space tug, will be launched into space in the year 2030. What makes this spaceship so unique is its power source, which is nicknamed Zeus. Zeus is like a moving nuclear power station, and it's going to generate a huge amount of energy to help push the spaceship through the vastness of space. Right now, if we wanted to send something to Mars and back, it would take over 3 years. But with this new nuclear-powered spaceship, NASA believes we could shave a whole year off that time. Imagine that. Exploring the mysteries of our solar system faster than ever before, thanks to the power of nuclear energy. It's going to revolutionize space travel as we know it. NASA is planning a groundbreaking mission. They aim to pair a powerful 10-kilowatt nuclear power plant with a lunar lander, setting course for the Moon by 2027. This venture marks a significant milestone, as the United States has never ventured into the world of space with a nuclear reactor on board. In contrast, Russia has already deployed over 30 nuclear reactors in space. This fusion of nuclear power and space exploration is not confined to lunar voyages alone. There are superb ambitions. Zeus, for instance, is envisioned to utilize a similar kilowatt nuclear reactor to leapfrog across planets, unlocking new horizons in interplanetary travel. The promise of nuclear technology, especially nuclear fusion, holds immense potential to revolutionize space exploration. Traditionally, spacecraft propulsion relies on various forms of propellants to generate force. Nevertheless, alternative propulsion methods exist, using the power of the sun itself. These innovative approaches challenge conventional thinking, hinting at a future where our journey through space may be powered solely by the boundless energy of our celestial neighbor. Solar sails have been under development for many years, but with advancing technology, spacecraft fueled by the sun are swiftly transitioning from theory to reality. SpaceX's launch of the LightSail 2 in 2019 marked a significant milestone in this journey. The LightSail 2, boasting a vast expanse of 344 square feet, utilizes sails crafted from resilient mylar, a material designed to withstand the difficulty of space travel. When the radion force emitted by the sun interacts with this specially seed sails, it generates pressure, propelling the spacecraft forward. The fascinating aspect lies in the versatility of this propulsion system. The speed at which the spacecraft travels hinges upon several factors, primarily the intensity of sunlight striking the sails. Consequently, the craft's velocity varies based on its proximity to a star. If it finds itself distanced from a celestial body, its movement becomes notably slower, highlighting the intricate interplay between cosmic forces and engineering ingenuity. How about we talk about warp drive technology? Just because you've heard that creating a warp drive might be really tough doesn't mean it's never going to happen. Actually, some scientists have just made a groundbreaking announcement. They say they've figured out how to make a warp drive actually work. In a recent paper, researchers claim they've cracked the code and developed a solid model for building a real-life warp drive. It's pretty exciting stuff. Numerous skeptics have dismissed the idea of warp drive technology as unattainable, arguing that it would demand an enormous quantity of unusual negative forces. The concept of warp drive, popularized by the renowned science fiction series Star Trek, illustrates the Federation's ability to surpass the speed of light through the use of a warp drive powered by the collision of matter and antimatter, resulting in immense energy release. However, the question remains: can warp drives exist in our reality? Our comprehension of warp drive theory largely comes from the pioneering work of theoretical physicist Miguel Alcubierre, whose groundbreaking contributions have become legendary in the field. This method of propulsion follows Einstein's theory of general relativity. It aims to enable travel faster than the speed of light by causing a local expansion of space-time behind the spaceship, while simultaneously inducing a contraction in front of it. However, the implementation of the Alcubierre drive requires an enormous amount of energy, possibly surpassing the total energy available in the entire universe. This energy is necessary to manipulate and screw up space-time ahead of the spacecraft, forming a protective bubble around it. If you were an astronaut aboard this spaceship encased within the bubble, you wouldn't perceive any sensation of acceleration. Indeed, this groundbreaking new physical model operates with minimal reliance on negative energy, a departure from its predecessor. It seizes upon the intriguing notion that space-time bubbles possess an inherent flexibility, allowing them to manifest in various behaviors. Nevertheless, it's crucial to recognize that at present, this remains purely theoretical. The sheer magnitude of mass requirements still looms as a significant hurdle. Yet amid these challenges, a tantalizing prospect emerges. While the dream of a tangible physical drive may seem distant, if not unattainable, both in our current era and perhaps even centuries hence, this newfound model instills a renewed sense of hope. The tantalizing possibility of warp speed travel draws sensibility nearer, shattering previous conceptions of its feasibility. The question then beckons: could we witness the realization of warp drive within our own lifetimes, or will such a feat escape from us for centuries to come? Thanks for watching another episode of Hyperspeed. While you are still here, make sure to click the video on your screen for more quality content.